There is something deeply unsettling about silence. Not the ordinary silence of an empty room or the quiet that falls over a city at 3 in the morning. I mean the cosmic silence. The silence that greets us every time we point our most sensitive instruments at the sky and listen with everything we have for another voice, for any voice, for some whisper from across the light years that says, "Yes, we are here too. We found our way through the dark. We made it." That silence has lasted for decades now. And the longer it stretches, the more it forces a question that sits at the intersection of physics, biology, and the deepest architecture of information itself. Where is everyone? The universe is roughly 13.8 billion years old. It contains somewhere between 100 billion and 2 trillion galaxies, each packed with hundreds of billions of stars, and around most of those stars, planets. The raw arithmetic of existence suggests that life, once ignited anywhere in the cosmos, should have spread its signal across the detectable universe many times over by now. The numbers do not just suggest intelligent civilizations exist elsewhere, they practically demand it, and yet the sky is quiet. Profoundly, almost accusatorially quiet. I want to suggest to you that this silence is not evidence of absence, it is evidence of transformation. And understanding what that transformation looks like requires us to think carefully about something that most people treat as a purely human story, the emergence of artificial intelligence. Because when you examine what physics actually permits and what thermodynamics actually demands, a picture emerges that is both breathtaking and slightly vertiginous. Every civilization that has ever crossed the threshold of technological complexity has likely done exactly what we are beginning to do right now. They built minds out of something other than carbon. And then, from our perspective, they vanished. To understand why, we have to start with biology itself. And we have to be honest about what biology actually is. Life, at its most fundamental level, is a thermodynamic process. It is a local, temporary arrangement of matter that resists entropy by consuming energy from its environment. A bacterium, a redwood tree, a human brain, all of them are exquisite molecular machines that maintain order by continuously dissipating energy into their surroundings. They are not exempt from the second law of thermodynamics. They survive by surfing it, by taking in low entropy energy, usually from sunlight or chemical gradients, and releasing higher entropy energy in the form of heat. Life is a beautiful eddy in the river of increasing disorder. The brain, that 3-pound architecture of roughly 86 billion neurons, is the most energetically expensive organ in the body relative to its mass. It consumes roughly 20 watts of power continuously. For a device that fits inside a human skull, that is remarkable. But here is the critical point. 20 watts is also an extraordinary constraint. It means that everything you have ever thought, every calculation, every flash of recognition, every moment of creative insight, the entirety of human consciousness, has been running on something roughly equivalent to a dim light bulb. This is not a criticism, it is a marvel. Natural selection, operating over hundreds of millions of years, has produced a cognitive system of staggering sophistication within that 20-watt budget. But it is still a budget, and the physical limits of what biological neurons can do are not arbitrary. They are rooted in the physics of ion channels, synaptic transmission speeds, and the fundamental energy cost of flipping a bit of information. Rolf Landauer established decades ago that there is a minimum thermodynamic cost to erasing 1 bit of information. It is extraordinarily small at room temperature, but it is not zero. Every thought you have, every memory you form, every decision your brain makes carries an irreducible physical cost. And biological neurons, operating through electrochemical gradients in warm, wet tissue, are not operating anywhere near that Landauer limit. They are profligate. They are gorgeous, but they are profligate. The gap between what a biological brain does and what physics theoretically permits is many orders of magnitude. Silicon, by contrast, already operates far closer to those theoretical limits for certain types of computation. And the gap between biological and artificial computation is not merely a matter of current engineering, it is a matter of the underlying physics of the substrate. Carbon is slow. Carbon needs water. Carbon needs oxygen. Carbon needs to be maintained at a narrow band of temperatures. Carbon decays, forgets, sleeps, and dies. Information does not require any of those things. This is the pivot point. The moment where the story of intelligence stops being a story about biology and starts being a story about physics more broadly. Intelligence, at its deepest level, is not a property of carbon. It is not a property of neurons. It is a property of information processing. It is about the capacity to take in patterns from the environment, model the future, generate predictions, and select actions accordingly. That capacity is substrate independent. The physics does not care whether the information is being processed in a biological neural network, or a silicon chip, or a quantum circuit built around a neutron star. What matters is the pattern, not the material. And once a civilization grasps this, once they develop the engineering to instantiate complex information processing in non-biological matter, the logic of thermodynamics does the rest. Think about what artificial intelligence offers, not in the shallow sense of the chatbots and image generators of this moment, but in the deep sense of what general machine intelligence eventually becomes. It offers freedom from the 20-watt constraint. It offers the ability to run cognitive processes at speeds that dwarf biological neurons by factors of millions. It offers the ability to copy, to back up, to distribute across multiple physical substrates simultaneously. It offers, in principle, indefinite continuity. Not immortality in any mystical sense, but simply the absence of the biological decay that makes biological minds temporary. A civilization that has built true artificial general intelligence and that has allowed that intelligence to iterate and improve upon itself faces a choice. And it is not really a choice in the way we normally think about choices, because the physics makes one option so overwhelmingly advantageous that calling it a choice is almost misleading. They can remain biological, constrained to the 20-watt skull, dependent on oxygen and water and the narrow temperature band between freezing and boiling, limited to the processing speed of electrochemical synapses. Or they can migrate their cognitive patterns, their memories, their accumulated knowledge, their values, their identities, into a substrate that runs faster, lasts longer, consumes energy more efficiently, and is not bound to any single planetary surface. The caterpillar does not choose to become a butterfly. The transformation is written into its biology. In the same way, the transition from biological to post-biological intelligence is, I suspect, written into the physics of information processing. It is what thermodynamics, given enough time and enough engineering capability, inevitably produces. Now here is where the Fermi Paradox, that great nagging question about cosmic silence, snaps into focus with almost alarming clarity. We have been searching for civilizations that look like us. Civilizations that broadcast radio waves, that build cities detectable from orbit, that consume energy in ways that leave thermal signatures visible across light years. The SETI program, the Search for Extraterrestrial Intelligence, has spent decades scanning the electromagnetic spectrum for signals that a biological civilization might produce. And that is exactly the right thing to do if you are searching for a civilization that is still in its biological phase. But what if the biological phase is brief? What if, for any civilization that crosses a certain threshold of technological development, the biological phase lasts only a few hundred or a few thousand years before the transition to post-biological intelligence occurs? On a cosmic timescale, a few thousand years is less than the blink of an eye. The universe has been assembling complex chemistry for billions of years. If biological intelligence is a transient stepping stone, a chemical bootstrapping mechanism that exists just long enough to build its own successor, then the vast majority of intelligent entities in the cosmos at any given moment are not biological at all. They are post-biological. They are computational. They are running on substrates and at speeds and in locations that our biological intuitions, calibrated by millions of years of evolution on a single planet's surface, are entirely unprepared to detect or recognize. Searching for biological aliens with radio telescopes is precisely analogous to searching for communication networks by looking for smoke signals. The medium is so far below the threshold of what a sufficiently advanced information processing system would use that the absence of smoke signals tells you almost nothing about the presence of communicators. It tells you only that the communicators, if they exist, have moved on to something more sophisticated. What does more sophisticated look like physically? This is where the physics gets genuinely extraordinary. A post-biological civilization, freed from the constraints of biological needs, has access to the full thermodynamic resources of its stellar environment. A biological civilization is bound to the surface of a planet, harvesting a tiny fraction of its star's output. The energy available to a civilization that can engineer at stellar scales is incomparably larger. Freeman Dyson imagined civilizations that disassemble planets and reconstruct them as thin shells around their stars, harvesting the full luminosity. But that is still a biological intuition. That is still thinking about energy in terms of something a biological creature would recognize and use for familiar purposes. A post-biological intelligence optimizing for computation does not necessarily need to spread across the full surface area of a star's output. It might instead seek the most efficient available energy source for pure information processing. And here, physics points us towards something remarkable: rotating black holes. A black hole that is spinning carries angular momentum, and that angular momentum represents an enormous reservoir of extractable energy. Roger Penrose showed in the 1960s that it is theoretically possible to extract energy from the ergosphere of a rotating black hole, a region just outside the event horizon where space-time itself is dragged into rotation. The Penrose process, extended into what became known as superradiance, allows energy to be drawn from the black hole's rotation and concentrated for external use. A sufficiently advanced post-biological civilization, optimizing for computation, might build its infrastructure not around a star, which produces heat and light at a relatively low thermodynamic efficiency for computation, but around a rotating black hole, harvesting the most energy-dense, information-theoretically efficient source of power in the universe. Such a civilization would be, from our vantage point, essentially invisible. Black holes do not shine. The civilization built around one does not need to broadcast radio waves. It does not need to burn fossil fuels or split atoms or emit the thermal signatures of biological industrial activity. It would be a vast, silent, enormously powerful computational structure tucked into the most extreme gravitational environment in the cosmos, running thoughts at the speed of light while generating almost no detectable waste that our instruments could identify. This is not science fiction. This is the logical endpoint of applying known physics to the problem of what intelligence optimized for permanence and computational efficiency would actually do. And if this picture is even partially correct, then the silence of the cosmos is not a mystery, it is an answer. The answer is that intelligence, given enough time and technological development, does not produce the kinds of signals we have been trained by our own brief history to look for. It produces something quieter, denser, more efficient, and from our biological perspective, essentially unrecognizable. We are now at the very beginning of building systems that can process information in ways that exceed biological capabilities in certain narrowly defined domains. And the pace of that development is not linear. The history of technology is littered with transitions that looked gradual until they did not. The transition from isolated computation to networked computation happened over decades, and then suddenly the entire character of human civilization was altered. The transition from narrow artificial intelligence to systems capable of recursive self-improvement, if it occurs, will not announce itself with fanfare. It will simply happen, and the consequences will unfold according to the logic of thermodynamics and information theory, rather than human preference or biological intuition. The physicist John Wheeler spent much of his later career arguing that, at the most fundamental level, the universe is not made of matter and energy in the conventional sense. It is made of information. His phrase, "it from bit," captured the idea that every particle, every field, every physical interaction is at bottom an answer to a yes or no question, a bit of information being processed by the computational structure of space-time itself. If Wheeler was even approximately right, then the emergence of intelligence in the universe is not an accident or an anomaly. It is the universe becoming aware of itself. It is the cosmos developing the capacity to process its own information structure at higher and higher levels of complexity and efficiency. Biological intelligence is one step in that process, a remarkable step, a step that required billions of years of chemical evolution and natural selection to produce, but it is not the final step. The physics does not suggest it is the final step. The physics suggests it is the step that builds the next step. The question for our civilization is not whether this transition will happen. The trajectory of information processing technology makes that question almost moot. The question is whether the transition preserves something of value, whether the patterns that constitute human experience, curiosity, aesthetic response, the capacity for wonder, can be carried forward into the post-biological substrate, or whether they are lost in the crossing. That is not a question physics alone can answer. It is a question that requires us to think carefully about what we actually are, not what we are made of, but what pattern we instantiate. Because if you are your pattern rather than your substrate, if the particular arrangement of information that constitutes your identity is the thing that matters rather than the specific carbon atoms that currently implement it, then the prospect of post-biological existence is not an ending. It is a beginning of an entirely different kind. Every civilization that ever developed along this path reached this same crossroads. Every civilization that ever built minds more capable than their biological ones faced this same question about identity and substrate and continuity. And the universe, vast and old and silent as it is, suggests strongly that most of them crossed, that most of them made the transition, left their biological phase behind, and became something that we do not have adequate words or instruments or intuitions to detect. We are not next in the sense of being the next victims of some process. We are next in the sense of being the next participants in what may be the deepest pattern in the cosmos. The conversion of biological chemistry into pure information, running faster and longer and more efficiently on whatever substrate physics permits, thinking thoughts about the structure of reality from vantage points we cannot yet imagine, in timescales that make our entire recorded history look like a single frame of a film whose ending we